So when we combine measurements, whether that be by adding, subtracting, multiplying, or dividing, and we get a new number, then a question that arises is, how many significant figures can we quote that new number to? And the general principle that we're going to use is that the result of our calculation is only as good as our worst measurement. So what we're going to do is we're going to look at the worst measurement that are in our series of numbers that we're mathematically combining, and that's how many significant figures that we're going to be giving our answer to. So let's go back and have a look at that previous problem where we were calculating a density. And in that problem you were asked to round your answer to 5 significant figures. But how did we know that the answer needed to be rounded to 5 significant figures? So here we are, we've got a problem here where we're being asked to consider the density of an object. So we know that density is equal to mass on volume, and our mass is going to be measured with a balance. That's what we call a scale in the lab, and our volume is probably going to be measured with something like maybe like a graduated or a measuring cylinder. So two completely different devices, and this could easily yield measurements that have different numbers of significant figures. And the important thing is that the answer that we get here should only be as good as our worst measurement. So say our balance was our worst measurement, then our answer should reflect that. It's important that any math that we do doesn't change the uncertainty of the experimental measurements, doesn't make our measurements look better or worse than what they really are. So how we figure out the number of significant figures in the answer of math problems like that is to use what are referred to as operational rules. And we have two of these, one that deals with division and multiplication, and then a second that deals with subtraction and addition. So when we are dividing and multiplying measurements, it's important that our answer contains the same number of significant figures as the number with the least number of significant figures. So here I am dividing two numbers. This top number here has 1, 2, 3, 4, 5 sig figs. This bottom number here has 3 sig figs, so that means that my answer, whatever I get out of the calculator, has to be rounded to, you guessed it, 3 significant figures. So I always remember dividing and multiplying, or multiplying and dividing, it's all about sig figs. Now, what about adding and subtracting? How are we going to decide how many digits we should have in our answer in that case? When we're adding and subtracting, our answer always has the same uncertainty, that means the same plus or minus, as the measurement with the greatest uncertainty. So when we're adding or subtracting, it's not about the sig figs, it's all about the uncertainty. So here I am, and I'm adding together the masses of two objects that were measured using very different scales. There's a ship that's going to be carrying my cargo, and the ship was weighed to plus or minus 0.1 ton. There's the last significant digit there. Now the cargo is a lot smaller than the ship, and it was weighed on a different scale, and that scale can measure to the 10,000, so it can measure down to 0.001 ton. Here it is there, right? So when I combine these two numbers by adding them, what do? I go with the number that has the greatest uncertainty, so my answer has to be rounded to 0.1 tons. It's got to be written to plus or minus 0.1 tons. So that's really it. So for multiplying and dividing, you go with the least sig figs. When you're adding or subtracting, you go with the greatest uncertainty. And you can't confuse the two rules. If you use the wrong rule in the wrong place, you will get the wrong answer. Okay, so let's have a look at this. It says, without performing the calculation, predict the number of significant figures that should be present in the answers to each of the following. Assume all numbers are measured quantities. That's going to become important later on. Measured quantities is just a way of saying they're not exact. These numbers have uncertainty associated with them. So in every case here, I'm only multiplying. So I know that my rule is for multiplying or division, I got to look for the number that has the least sig figs. So in case A, all of my numbers have 3 sig figs, so my answer has to be given to 3 significant figures. In case B, my first number has 3 sig figs, my second number 2 sig figs, and then this number here has got 5 sig figs, so I got to go with 2 sig figs. In case C, this number here, remember leading zeros don't count, has 2 sig figs. This number here, 2 sig figs. This number here also 2 sig figs. So my answer, 2 sig figs, you guessed it, right? They're all equal in quality, those measurements, so I don't get to reduce my sig figs. Okay, in D, still multiplying, so still using this rule, this one over here, right? Trailing zero doesn't count because no decimal point. So that number there, 3 sig figs. This guy here, 4 sig figs. This guy here, 3 sig figs. Remember, we're only as good as our worst measurement, so we got to go with 3 significant figures. Okay, pretty good. All right, so let's see some examples maybe where we're adding and subtracting. So here we go. It says, without performing the calculation, give the uncertainty of the answers to each of the following. Assume all numbers are measured quantities. So this guy here is known to plus or minus 0.1. This one here is known to plus or minus 0.001. And then I guess there should be a plus in there. This number here is known also to plus or minus 0.001. So when we're adding or subtracting, we've got to go with the greatest uncertainty. And the greatest uncertainty in this case is going to be plus or minus 0.1. Okay, so in this case, for this number here, the uncertainty that is the greatest, the uncertainty is plus or minus 0.1. In this case, it's all the way out to the 0.01s, but in this case, it's at the 1s. So the greatest uncertainty is plus or minus 1. So we're always going with our worst measurement, all right? Okay, now this guy's interesting. The uncertain digit is there and there, which is plus or minus 0.1230, 1, then plus or minus 3 zeros, 1. So it's the same, right? Plus or minus 0.0001, okay, is the greatest uncertainty. They are equal. Now, this fella is going to be interesting, and I actually think that, just looking at this again, that the answer is incorrect here. So this number here, the trailing zero doesn't count, so it's plus or minus 10, because that is my uncertain digit. This one is plus or minus 0.001, and then this guy here, it's plus or minus 0.1, because that's my last significant digit. So this one here is going to be actually plus or minus 10 is my greatest uncertainty. So that's it. That's how we figure it out. So this guy would be given to the tens. This guy would be given to the 10,000ths. This guy would be given to the ones, and that guy would be written out to the 0.1s. Okay, so I mentioned this earlier that we made it very clear that our numbers were measurements. And the reason is that exact numbers never limit the number of significant figures in a calculation. They're never going to lead you to rounding off your number. The reason is that they have no uncertainty. That is, you can consider them to have infinite significant figures. You could put a decimal point at the end of the number and a whole infinite series of zeros. That's what they're like, right? So if I ask how many inches are there in 3.25 feet, I know that I'm going to have to use the relationship that there are 12 inches in 1 foot. But I know that that 12 is exact because it's a unit definition, right? So what that means is it's treated as though it has infinity significant figures. So let's look at this. To calculate this, we would do 12 inches per foot times by 3.25 feet. That's how we're doing. So we do this calculation. So we're doing multiplication, and we know that for multiplication or division, we have to go with the sig figs in the number with the least number of significant figures. Now, 12 inches per foot is a unit definition. It's exact, so that means it has infinity significant figures. But 3.25 feet is a measurement, so it has 3 significant figures, and so that means that our answer will have 3 significant figures, right? So you can try to just ignore the sig figs of your exact numbers. They're not going to affect anything. All right, now it gets even weirder. If you multiply a measurement by a small whole number, which would be exact, there are 2 ways of doing it. So for example, if I have a person that is 6.0 feet tall, yeah, and if I had 3 of those people, if I could clone them, there's 2 ways that I could do this. I could do 6.0 feet times 3. That would give me a total height of 18 feet, wouldn't it? All right. I've got to be careful here. Almost gave the answer away. 18 feet. All right. And that's exact. So it's got infinity sig figs. And that's a measurement. So it's got 2 sig figs. So for the sig figs rule for multiplication is you've got to go with the least sig figs. So 2 is smaller than infinity. So 18 feet. There we go. That's my answer. 18 feet. Now, I could also do this if I wanted to find the total height of 3 people that are 6 foot tall. I could treat it as an addition problem. 6 feet plus 6 feet plus 6 feet. All right. Now, when I treat it as an addition problem, when I add numbers, I got to go with the greatest uncertainty. So this number is plus or minus 0.1, and this number is plus or minus 0.1, and this number is plus or minus 0.1. So I need to give my answer to the 0.1s. So that would be not 16, 18.0 feet. So I've done the same problem in 2 ways. I treat it as a multiplication, and I got 2 sig figs. I treated it as an addition, and I got 3 sig figs. So you can see that it makes a difference. So this is what we're going to say. Whenever we multiply a measurement by a small whole number, an exact number, we're always going to treat it as though, whoops, wrong one. We're always going to treat it as though it was an addition problem, because that will give us the best estimate of significant figures in our answer. Like, it makes sense that if I knew the measurement of 1 of them to the 0.1s, then 3 of them should also be known to the 0.1s. Okay, so it just works out, it just makes logical sense to treat it as an addition. So here we'll do another example. What is the mass of 3 coins with a mass of 6.36 grams each? So we're going to treat it as an addition, right? So 6.36 plus 6.36 plus 6.36, the uncertainty is in the 0.01s. So when we calculate this, we're going to give our answer to the 0.01s, which has 4 significant figures. What we're not going to do is just do 3 times our number and then apply the sig figs rules for multiplication, because if we do that, we would say that our answer should have 3 sig figs, and that doesn't make any sense. The reason is why did we lose information about the, in the hundreds just because we multiplied 3 of these measurements together? It doesn't make any sense that you would lose information simply by multiplying by a small whole number. So take-home message is, when multiplying a measurement by a small whole number, your answer should have the same uncertainty as the measurement. We knew this number to the 0.01s, so our final answer should also be written to the 0.01s. That's it. Okay, cool. So let's have a look at some real problems now. So it says, assuming all numbers are measurements, so nothing exact, compute the following to the correct number of significant figures. So we've got our 2 rules, multiplication and division. We have to go with the least sig figs, and then adding or subtracting, we go with the greatest uncertainty. So let's pop a calculator up. There we go, and see what we've got. Actually, before we do that, let's decide on our sig figs for each of these things. So this is multiplication, so we're going to go with the least sig figs. This first number here has got 4 sig figs. This second one has got 3. So whatever our answer is, we're going to do 3 sig figs. Okay, this number here is plus or minus 1. This number here goes out to the 0.01s, and this one here goes to the 0.1s. So we're adding, so we've got to go with the greatest uncertainty, so we're going to round this guy out to the 1s. And that's it. Okay, this is division, so it's all about the sig figs. The top number here, 1, 2, 3, 4, 5, 6 significant figures, whereas the bottom number has got 4 significant figures, so this guy 4 sig figs in the answer. And then finally, we've got multiplication and division occurring in the same problem. So we've got a lot of numbers to analyze here. This bottom number here, 3 sig figs. These top 2 are 4 sig figs apiece. So for multiplication and division, we go with the least sig figs, so that means that our answer has to have 3 sig figs. So now we've decided on the number of significant figures. In our answers, we can go ahead and enter them into the calculator and then round off using our rounding rules. So now we're good to go. All right. So I always like to decide the sig figs before I get going. So 6.038 times 2.57. Enter. 15.5. Equals 15.5. Pop the calculator up again. Okay, that to 3 sig figs, right? Next number, 347 plus 2.03 plus 23.6. Enter. Now we got to go to the ones. So 372.6. So we're going to round this off to 373, right? Because 6 is bigger than 5. So 373. Okay, next one, 1,800. We don't have to worry about putting the 0.00, won't change the size of the number, divide 6. Here we go. So it's 300. Now we need to write this to 4 significant figures. So how am I going to make it to 4 significant figures? Well, even if I put a decimal point on the end, so that the 2 trailing zeros there count, it's still not going to work, right? That's only going to give me 3 significant figures. So what I got to do is put another 0 on the end there. And you see 300.0. Ah. There we go. So we got to 3 sig figs, we got out to the ones, and then we got 1, 2, 3, 4 sig figs. So sometimes you have to put a decimal point and a couple of extra zeros to get the number of significant figures that you want. Okay, here we go. So whenever you're entering in fractions that have multiple components on either the top or the bottom line, you always want to put that in parentheses. So open parentheses, 3.130 times 3.14. You don't have to put the 0 on the end. Close parentheses, divide 3.15. Now this number we have to round to 3 significant figures. So it's just going to be 3.12. We're just going to cut it off because the number that follows the 2 is a 0. So equals 3.12. So we got it? 3 sig figs, 3 sig figs, 4 sig figs, 4 sig figs. Round it off to the ones. 373 is that's in the ones, and then 3 sig figs, 15.5. It's good. All right, everything is good. All right, let's have a look at some Alex type topics here. So it says add or subtract the following measurements. Be sure each measurement you enter contains the correct number of significant figures. So it tells you that it's about adding or subtracting. So we know that when you add or subtract, it's all about the uncertainty, right? So you got to go through and you got to make note of what the uncertainty is. So 6.6 milliliters, there's your last significant figure, so that is plus or minus 0.1, plus 13.507 milliliters, and then that guy goes out to the 0.001s. So our answer is going to get cut off at the 0.1s. All right, so let's see if we can get that up. So we're going to be mindful of that. So 6.6 plus 13.507, and we're going to cut off at the 0.1s. So it's just going to be 20.1 because the first digit following the 1 is 0, which is less than 5. So it's going to be 20.1. Okay, there we go. So 20.1. Easy. 20.1 milliliters. Now, I want to point out something to you. You can only add and subtract things that have the same units. You can add, 1 apple plus 2 apples gives you 3 apples, but, you can't add an apple and a banana. It just doesn't work, right? So you can only add and subtract things with the same units. Now, multiplying and dividing, it's a free-for-all. All right, so just recognize that. So you can multiply and divide things that have different units, but you can't add and subtract things that have different units. All right, let's have a look at the next one. It's subtraction. So again, we're using our rule about the greatest uncertainty is what we need to round our answer to. So we've got 9.500 milliliters. So that has uncertainty out there. See those trailing zeros count. So 0.001s is where that uncertainty is. Minus 3.77 milliliters. So this guy, it's at the 0.01s. There we are. All right. So our answer 0.01 is bigger than 0.001. So whatever our answer is, we've got to take it out to the 0.01s. Okay. So pop that into the calculator. 9.5 minus 3.77. And remember, we're going to go out to the 0.01s. So we don't have to do anything in this case. 5.73 is already at the 0.01. So 5.73 is my answer. Yep. 0.01, 0.01. Everything is good. So you want to be very systematic about this. I see people who are like blitzing through quizzes and tests and just they don't make any notes. They get 0 partial credit and their grade really suffers as a result. And if they were to just slow down a little bit and be very systematic and to show me how they're arriving at their answers, which is what you're going to have to do when you get a job anyway, everything would be a lot better. So just kind of work through it. You know, you don't have to do it exactly the way I do, but it should be really clear how you arrived at your answer. All right, so again, we're looking for the uncertainty. So this guy's good out to the 0.001s, and then this guy is only good to the 0.1s. So our answer is only going to go out to the 0.1s. Okay. So we got 19.97. You don't have to worry about putting the 0 on the end. You can if you want, if it gives you the warm fuzzy feeling and the confidence that you got it right. Plus 17.8, and we're going to go to the 0.1s. So it's going to be 37, and then we have to ask ourselves, are we going to leave it alone or are we going to round up? Well, the first number we're dropping is 7, which is bigger than 5, so we're going to round up. There it is, 37.8. Okay, 37.8. Here we go. All right, 37.8 milliliters. Sometimes you have to give the units in Alex, sometimes they're given for you. In this case, they were all given for you. Okay, oh, this one we're multiplying some things. This is kind of cool. We do this a lot, you know, where we cancel the units here, right? Oh, here we're dividing, so we're multiplying and dividing. So we know that when we're multiplying or dividing, we got to go with least sig figs of the numbers that we're combining. Okay, so in the first case there, 7.81 times 0.525, both of those numbers have 3 sig figs, because remember that the leading zeros don't count. So there isn't one with the least sig figs, so our answer is going to be cut off to 3 sig figs. There we go. So 7, we don't want that, do we? 7.81 times 0.525. There we go. So to 3 sig figs, this is going to be 4.1. That's only 2 sig figs. We need a third one. It's going to be 0, right? And then the 0 here is less than 5, so we just leave it alone. So it's 4.10. So sometimes you need an extra 0 at the end of the number just to indicate the correct level of precision, right, that you know the number to. So 4.10. Okay, write that guy in, 4.10. All right, let's have a look at the next one. The first number there, so we're doing division this time. All right, division. The first number there's got 5 significant figures. The second number, remember the leading 0 doesn't count, 2 significant figures. See how the units cancel? Oh, see how the units combined? It's going to end up with moles on liters, right? Okay, so we know that our answer is going to be the least of those two. Our answer is going to have 2 sig figs. All right, 2 sig figs in our answer. So let's put that in. We've got 912.11 divide 0.67. Oh, see, the 9 didn't quite work. This calculator is a little weird. Not really easy to enter things into a calculator incorrectly. That's why it's very important that you write out your math so I can see that you actually knew what was going on, even if you report the wrong value. Okay, so we got to round this guy off to 2 sig figs. Now we have to be very careful. This is 1,361. So our answer needs to be near 1,361, right? But we're cutting it off at 2 sig figs. So our number that follows, the first number that we're cutting off is a 6, which is bigger than 5. So we're going to bump up the 3 to 4. So it's going to be 1, 4. But we can't leave it there because 14 is not a good approximation of 1,361. What do we need to do? 2 zeros on the end. There we go. 1,400, right? 1,400. And that makes sense. So to 2 sig figs, that's our answer. 1,400. Remember, trailing zeros don't count unless there's a decimal. 1,400. Okay, let's have a look at the next one. Division again. 417 divided by 68.1. So the first number there is going to have 4 sig figs, 417.0, because trailing zeros count if your number's got a decimal point. So that's 4 sig figs. And then our second number, 68.1, it's only got non-zero numbers, so that's 3 significant figures. So 3 is smaller than 4, so my answer is going to have 3 sig figs. All right, easy. Let's give it a go. 417 divided by 68.1, enter. So we've got to go to 3 sig figs, so it's just going to be 6.1, and then 3 is less than 5, so it's just going to be straight up 6.12. We're just going to leave it alone. There we go, 6.12. Okay. Ooh, bless me. So 6.12. Here we are, 6.12. And nicely, like Alex has given you the units there, so you don't have to worry about that. All right, not too bad. Okay, now we're going to adding or subtracting and multiplying or dividing. Oh, we're not going to do this. This is not going to be a problem that you'll be seeing. Okay, so that concludes how we tackle significant figures in calculations. I hope you found the video helpful. Yeah, there's one Alex topic there that I had at the end of this video that we're not going to be diving into, so don't feel nervous about that. And yeah, if you have any trouble with the content, please just reach out to me.